So today we will go through week 2 of superstructure part, and in the lecture of week 2 or in the week 2 content, we have some objective like knowing some information about the terms weight, force, mass, and gravity, and what is the difference between density and unit weight, and some explanation about the loads and load distribution, and calculating some of dead load of the construction material available in the Australian market, given by the Australian Standard 1170.1 version 2002. And I hope you have tried to access the standard using the new provider, Engineering Workbench. So if you click on this link, so this link will transfer you to the Workbench link, so you can access the standard using this link. So it is important to be familiar with the standard from now, so you can use it during the project. Okay, and also you have some tasks to do this week, so you can watch some of the videos that help you to understand more the terms of weight, force, gravity, and some of the trigonometric ratios like sine, cosine, and so on. And also have a look on the Australian Standard Structure Design Actions, Permanent, Imposed, and Other Action, which is 1170.1. And also here is some tables or design capacity table of steel like and roof sheeting. So roof sheeting, purlins, universal beam, and universal column members. So all these tables we will be using during the project as well. So it is good to have a look on them. And today we will start looking at our second lecture of this course, which is about loads, especially, and we will focus on dead load or permanent loads. So I will start sharing the slides now, and I hope you have accessed the slides. So these are the slides of week 2, structure actions or loads. So here is an example of a simple building or a simple structure to see how the structure transfers the load through its member. So as you can see here, we have a slab, like this is a slab. Okay, so this is our slab, and we have beams. So we have some beams, 4 beams on the 4 sides, and also at the corners we have columns. So we have slab, beam, column, and at the bottom we have footing, and then all this is resting on soil. So how the load transfer through the building and up to reaching the soil? Because this is the philosophy about how the load transfers. So if we have gravity load like person load or any load like that, so this load will transfer in 2 directions to the beams. So the slab load will transfer in 2 directions to the 4 sides or the 4 beams. Then the beam will transfer the load in this direction to the column, and also other beam also transfer the load to the column. So the load transfer from slab, then to the beam, then the beam transfer to the column, then the column will transfer this load vertically. So the 4 column will transfer the load vertically to the footing. Then the footing will transfer this load to the soil. Okay, so if we ask you about the sequence of this load transfer or how the load transfer, so the gravitational, which is vertical load, will transfer from slab to beams, then to columns and footing, and finally to the soil. Okay, so the load transfer from slab, the first one, to the beams surrounding the beam, and then to the column. Sorry. And then to the footing, and finally to the soil. So this is the sequence of load transfer for vertical or gravitational load. For the lateral load, it is a different approach, depend on what is the system to resist the lateral load, and we will uh, leave this to the next lecture or coming lectures. Okay, so this is for the gravitational load path and how the load distributed and how the load transferred through the members until reaching the soil. So our rule when we designing a building or designing a structure, how the load will transfer from the top of the building to the soil. And here is the sequence of how to transfer the load. Okay. And here is a short video to show us what is the differences between weight, force, mass, and gravity. So I will open this video for you so you can watch it. Okay. So okay, so you can't hear the video. The volume is too low. Okay, well, try to. So my volume was good. My voice volume was good. Only the video. Okay, so I will try now. Can you confirm? Is it better? Still can't hear. Okay, so I will.
Let's add the bag of sugar. It shows the weight is almost 10 newtons. Can you remember?
Okay, guys. So no. Okay, guys. So I will try it now again. Last time. Can you hear me now? Yep. Okay, that's good. So we'll try the video. Please confirm you are hearing the video as well.
Sugar.
Can you hear the
It
video
shows
now?
the weight is almost 10 newtons. Can you remember the
Okay,
equation
thank
that
you.
links mass with weight? Remember F equals ma, where F is force in newtons, m is mass in kilograms, and a is acceleration in meters per second. We can rewrite this a little as W equals mg, where W is weight in newtons and g is acceleration due to gravity. On Earth, g equals 9.8 meters per second. So the weight of the 1 kilogram bag of sugar is 1 times 9.8, which equals 9.8 newtons, as the picture shows. Often in everyday life, we use the word weight, when in fact we mean mass. The bag of sugar has a mass of 1 kilogram, but a weight of 9.8 newtons. Now let's take this bag of sugar to the moon. The moon is much less massive than the Earth, and so has a lower gravity. On the moon, g is only 1.6 meters per second. See how the weight has dropped compared to when it was on Earth. But notice, we still have the same amount of sugar. There is still 1 kilogram of stuff. The weight has changed, but not the mass. Jupiter, the gas giant, has a G value of 25 meters per second. Can you work out what the force meter would show for the bag of sugar here, assuming there was a solid surface to stand on? The sugar now has a weight of 25 newtons. But don't forget, we still have 1 kilogram of sugar. That hasn't changed. Do you remember gravity? Watch this video. An object thrown away from the Earth will experience a force towards the Earth which slows it down, stops it, and the object accelerates back towards the Earth. This acceleration is due to the Earth's gravitational force and is written as a little g. It's also known as the gravitational field strength. To stop the apple falling, so to prevent the gravitational force pulling it toward the center of the Earth, a force is needed that is equal to this gravitational pull. Remember this. And on Earth, G equals 9.81 meters per second, or approximately 10 meters per second. Okay, back to mass and weight. Remember that mass is a measure of the amount of stuff in an object and gives a measure of how difficult it is to get moving or to stop it. It never changes. For example, my mass on Earth is 56 kilograms. On the Moon, I would still have a mass of 56 kilograms. The acceleration due to the Earth's gravity is measured in meters per second, or it can be measured in newtons per kilogram, as it's a force exerted on a unit mass. So let's now use this lovely equation to find my weight. Weight is the force due to gravity, and that depends upon the masses of the two objects that are attracted. On Earth, my weight is mass times gravity, so roughly 56 kilograms times 10, which is 560 newtons. But what about on the Moon? The gravitational acceleration on the Moon is only 1.6 meters per second. I hope you got 89.6 newtons. So, you would feel very light on the Moon, and if you tried to walk, each step would send you leaping away from the surface. See how gravitational field strength changes on the surface of different planets. This is because the planets have different sizes and masses. The largest planet, Jupiter, with the greatest mass, has the highest gravitational field strength. My weight on Jupiter, if there was a solid surface to stand on, would be 1,400 newtons. And bathroom scales, which are calibrated in kilograms, would show I had a mass of 143 kilograms. You would feel very heavy, yet your mass would still be 56 kilograms. Just your weight would be 2.5 times more than on Earth. Now for Newton's apple. An apple with a mass of 100 grams is held in your hand to stop it from falling to Earth. What force do I need to prevent it from starting to fall? Take the acceleration due to gravity to be 10 meters per second. Pause the video and work this out. So the force is mass m times g, or 0.1 kilograms times 10. So the force of gravity on an apple is about 1 newton. And it was the falling apple that gave Isaac Newton the idea in the first place. How about that? And just remember, our mass always stays the same, but our weight can change. Maybe we should all move to the Moon.
Thank you, guys. So I hope you have understand the difference between mass and weight and gravity. So the mass is a constant value for each body or each structure, but the weight depend on where we are like on the moon or on the Earth or on the Jupiter. So the gravity acceleration for each planet is different, which affects the weights, but the mass is all constant. Okay. So this just was a short video to explain the difference between the terms, and now we can have some example about that. So what is a kilonewton? A kilonewton is, or the Newton is, we have Newton as a unit and kilonewton. Okay. So Newton and kilonewton are forces unit or weight unit, not a mass unit. Okay. So to know what is a kilonewton or what is Newton, so using Newton's second law of motion, the second law of motion by Newton is force equal to mass time acceleration. So the force is mass time acceleration. So the force in Newton equal to the mass in kilogram times acceleration in meter per second square or per second. So if we have the force in Newton equal to the mass in kilogram times acceleration per second, this means that 1 Newton this means that 1 Newton as a unit equal to 1 kilogram times the gravity acceleration 9.81 meter per second square. So 1 Newton equal to 1 kilogram times 9.81 meter per second square. This is our 1 Newton. To find an example of 1 kilonewton, if we have like a footy player, his mass is 102 kilogram. So his weight will be 102 kilogram times the gravity acceleration, 9.81 meter per second, and divide by 1,000 to get it in kilonewton. This will be equal to approximately 1 kilonewton. So if we do this calculation here, so the weight of the player will be 102 kilogram times 9.81 meter per second square. This will give us a value of 1,000 Newton. To convert this 1,000 Newton to kilonewton, we divide by 1,000, so it becomes 1 kilonewton. Okay, so this is the idea behind this explanation. This is just an example of 1 kilonewton. So the more important thing we need to know now is the relation between the force and mass and the acceleration, and the relation between 1 Newton and kilogram. Because in some times or in some cases, we need to convert the mass or the kilogram value to Newton value. So here is the explanation using the Newton's second law of motion. Okay. Do you have any question, guys, about that? All good? Okay. So let's move to the second concept we need to know, which is the density. So what is the density and what is the definition of the density? So the density is the mass per unit volume of a substance. So if we have a volume of a material like timber box or timber concrete block, concrete block or whatever the material is. So we know the volume of this substance. The mass of this volume will give us the density. So this is the definition, the scientific definition of the density, the mass per unit volume of a substance. So if we have a box, for example, of whatever the material or a block of a material, this block size is 1 by 1 meter by 1 meter by 1 meter, or whatever the unit is. So the mass of this block will be our density. So the formula for the density, as you can see here, rho equal to mass over volume. So density rho equal to mass per volume. The unit of density is kilogram per cubic meter. We need this formula because the construction material we will be using has different density or different weights, the unit weights. So we need to know what is the density of the material so that we can find how this material apply loads on the structure. So this is important to know, or when we do the analysis or the design of the structure, to know what is the density of the materials we are using in the structure. So for example, if we have a timber box with a mass of 30 kilogram and a volume of 20,000 millimeter cubed, so the density of this box will be the density equal to mass over volume. The mass is given as 30 kilonewton, 30 kilogram. The volume is 20,000 millimeter cubic. So when we divide the two values over each other, so we have 0.0015 kilogram per cubic millimeter. And if we want to convert it to kilogram per cubic meter, it becomes 1500 kilogram per cubic meter. Okay? So this is an example of how to find the density of a substance or density of any object or any construction material we will be using. Okay, so now if we jump to the next one, so we have another video to explain the density concept. So I will give you some time to watch this video.
Topic: density. Why does oil float on water? Don't know the answer? No worries. We shall find the solution. Realize that a large log of wood floated on water, but a comparatively smaller piece of rock sank. How is this even possible? This is possible because of density. It is the measure of the mass of an object per unit volume. In the first case, the log of wood floats on water because it has less density than water. This means that the amount of mass present in unit volume of wood is less than the amount of mass present in unit volume of water. However, in the second case, the piece of rock sinks because it has more density than water. This means that the amount of mass present in unit volume of rock is more than the amount of mass present in unit volume of water. Do you know why the helium-filled balloon is rising up in the air? This is again because of density. The balloon consists of helium gas, which has less density than the surrounding air. Hence, it rises up. Here, have a look. Oil is floating on water. Are you assuming that this is because of density? Yes, you are right. Oil has less density than water, hence it floats. However, there is another reason due to which oil floats on water. The reason is that both oil and water are immiscible liquids. That is, they do not mix with each other, even if we shake them. They separate out into two layers when kept undisturbed for some time.
Okay, guys, thank you for watching the video. And this shows a definition of the concept of density. So now we have a quite similar concept, which is the unit weight. So the unit weight and density are quite similar terms. We need to know what is the difference between them. So the unit weight, also known as the specific weight of the material. So this can also be named as specific weight, which is the weight per unit volume of the material. So the density is the mass per unit volume, and the weight is the unit weight is the weight per unit volume. So this is the differences between density and unit weight. Density, mass per unit volume. Unit weight is weight per unit volume. So the formula of unit weight is, as you can see, unit weight is weight per volume. So unit weight equal to weight per volume. And density is mass per volume. So they are quite similar concepts, but just slight differences. The unit of the unit weight is kilonewton per cubic meter. So unit weight is kilonewton per cubic meter, and if you go back, the density was kilogram per cubic meter. So this is the main difference, the unit as well. So another example, if we have a block of cheese with a mass of 3 kilogram and a volume of 3200 millimeter square. So the density will be equal to 3 kilogram over 3200 millimeter square. So the density will be 0.0009375 kilogram per cubic millimeter, or 0.09375 gram per millimeter cubed. So to convert from kilogram to gram, we multiply by 1000. So this is just to define the number. So the unit weight of this cheese block or cheese block will be the weight of the cheese block divided by the volume. So to find the weight is the mass times gravity acceleration. So this is the weight, 3 kilogram times 9.81 meter per second squared. So this is the weight. So if we divide the weight over the volume, we get the unit weight. So the unit weight of this material or this cheese is 0.0092 Newton per cubic millimeter, but the mass was, the density was 0.009375 kilogram per cubic meter. So this is the differences between the two concepts or the two terms, density and unit weight. And here is again or a summary of what is the differences between the unit weight and density. So the density is the mass per unit volume of a substance. The unit weight is the weight per unit volume, which means taking into account the gravitational force. Okay, so because the standard sometime or the provider of the material sometimes give you the probabilities of the construction material as density or as unit weight. So you need to know what is the differences between both, so that when you use them in the calculation, you understand how to convert between them. Okay, so now this is our part which is important for us as construction manager. So what is the unit weight of construction materials? So the construction materials are given in the Australian Standard 1170.1 version 2002. So the Australian Standard 1170.1 2002, this one here, give us the unit weights of the construction materials available in the Australian market. You can access the standard using this link by Engineering Workbench. So you can have a look on that, and we will go through them now. So this is an example of some materials given by the standard. So the unit weight or the material unit weight are given in table A1 and table A2 of the Australian standard, but mainly the unit weight is mainly in table A1 in the Australian standard AS 1170.1. So as you can see, for example, if you are using aluminium as a material, so the unit weight of this aluminium is 26.7 kilonewton per cubic meter. For example, if you are using timber, radiata timber, so the unit weight of this radiata timber is 5.3 kilonewton per cubic meter. So this all material you will be using in your field work or construction. So you can, if you need any weight of any unit weight of the material, you can refer to this table in the Australian Standard 1170.1 and find out what is the unit weight of this material. Okay, we will use this in our calculation in the tutorial and also in the project, and we will see some example now on that. Okay, and now we need to go through the loads to know what is the difference form of loads we can have on a structure. So as you can see, we have two main type of loads. As you can see, we have point load, and in other cases it can be named as concentrated load, and also distributed load. So as you can see here, this worker here, or this tradie here, is applying a unit weight because, or a buoyant load at this point of the roof. So this can be considered as a buoyant load. But as you can see here on this roof, we have a lot of birds, or maybe we have snow, or we have rain. So this type of loads are distributed over area or over line. So it can be named as distributed load. So this just some differentiation between, to show the difference between the buoyant load and the distributed load. And now we can go in details what is the differences between buoyant load and the distributed load. So a force, the buoyant load or the concentrated load, is a force that is applied at a single point along the structure member. So it is only applied at single point. So this force is zero dimension, means it is only at one point, and therefore measured in Newton or kilonewton. So similar to, again, this tradie here. So we have the load here. Or for example, if we have a beam like this, so this beam, we have one applied load somewhere on this beam. So it is applied at a point. So this is a point load. The unit of point load is Newton or kilonewton. Because Newton and kilonewton are the units of loads, so you can use either of them. So Newton and kilonewton. Okay. So this for buoyant load or concentrated load, and here is one example of buoyant load. So for example, what is the weight of this concrete block? So if we have a concrete block of this dimension, like 40 centimeter times 60 centimeter times 3 meter high. So any substance or any object that have volume, so it has weight, or has weight like this one. So what is the weight formula? The weight formula is W equal to the volume V times the unit weight gamma. Okay, so weight equal to volume times unit weight. Where does this come from? Because just before this slide earlier today, we mentioned that the unit the unit weight equal to weight over volume. So now if we want the weight, so the weight will be equal to this one times this one. Yeah. So it will be volume times unit weight. So the weight equal to the volume times the unit weight. So for example, here to find this weight of this block, so the first thing is we need to find what is the unit weight of concrete. So from table A1 from the Australian standard, the unit weight of concrete is 24 kilonewton per cubic meter. So this is the first information we have from the Australian standard. The other thing is the volume. What is the volume? The volume is the volume equal to the width times the length times the height. So if we consider this as length, this as width, and the 3 meter is the height. So the volume is the product of width times length times height, which is 40 centimeter, but because this meter, so we need to convert all of them to meter. How to convert from centimeter to meter? To convert from centimeter to meter, we need to divide by 100, because 1 meter equal to 100 centimeter. That's why in this formula here, I convert 40 centimeter to meter by dividing over 100. Times 60, also divide by 100 to convert from centimeter to meter, times 3 meter. So the total volume of this concrete block is 0.72, which is the product of 40 over 100 times 60 over 100 times 3 meter. Okay, so now we know the unit weight of the material and the volume. So the weight of this block, V times gamma, equal to 0.72 cubic meter times 24 kilonewton per cubic meter. Is that correct? So can we multiply cubic meter by kilonewton over cubic meter? Do you have any idea about that? So we have kilonewton over cubic meter times meter cubed. Okay, so the meter cubed will omit the meter cubed, so we will have the final unit as kilonewton. So when we multiply 0.72 times 24, this gives us a value of 17.25. The main thing here is the unit, because the units are important in our calculation. So kilonewton, because we multiply again meter cubed times kilonewton over meter cubed. So meter cubed omit meter cubed, we still have kilonewton. So the value is 17.28 and the unit is kilonewton. Okay. Do you have any question, guys, about that? Any question? No? Okay. So now we can jump to the next type of loads we have. So the second type of loads we have is the uniform distributed line load. So we have uniformly distributed live load, which is it also named as, can be abbreviated as UDL. UDL applies constant or equal force per unit length. So the UDL is force per unit length. So it is like kilonewton per meter. So we apply force per unit length. So which is common in our structural analysis design of beams and columns. So when we do the analysis of beam and columns, for example, under wind load, so we need to find the forces as distributed load over beam or over the column. So that's why it's important to know the uniformly distributed load, line load. So as you can see here in this example of beam here, so we have a beam and we have this uniform load here. So the uniform load is distributed over the beam span L. So we have the load Q and the beam span L. So as you can see, the load is not subjected or applied at one single point, but the load is applied over the whole length of the beam. Because it's applied over the whole length of the beam, it's called uniformly distributed line load. The formula for the UDL is force by length, and the unit is kilonewton per meter or newton per meter, but usually we use it as kilonewton by meter, because kilonewton and the newton are unit of forces, so you can use kilonewton per meter for uniformly distributed load. And here is another example of calculation of weights and uniformly distributed load. So for example, if we have a black butt timber beam like this, the length of this timber beam is 7.8 meter. The width of this beam is 20 centimeter. The height of or the thickness of this beam is 30 centimeters. So we have 3 dimensions of the beam: 20 centimeter, 30 centimeter, and 7.8 meter. The question is, what is the weight of the given black butt timber beam per unit length? So how can we find the weight of this beam per unit length? So the first thing is to find the weight of this beam. Then we can distribute it over the length. So from the previous example, the concrete block, we know that the weight of the object equal to the volume times unit weight. So here we need to find what is the unit weight of the material we have. So we have black butt timber. If you go to table A1 of the Australian Standard 1170.1, you will find that the unit weight of this material is 8.7 kilonewton per cubic meter. So this is our first part of the formula. Second part of the formula is our volume, V. So again, we have centimeter and meter. So we need to have all the units consistent. So to make the unit consistent, we need to convert 20 to meter by divide by 100, and the height 30 by 100 to convert to meter, and already the length of the beam is 7.8 meter. So we can find the volume of this beam as 0.468 cubic meter. Sorry, Julian? Or yeah, sorry, Julian. What you mean by says unit in weight says unit weight 7.84? Ah, yes. Sorry, maybe this is just a typo. I will update it. Thank you. So we have here just this one need to be updated, or I will update this one. Thank you, Julian. So it is just a typo here. So I will update this value. So the value is 8.7. So now after we find the volume 0.468 and the unit weight 8.7, so the weight will be V times gamma, which give us the total weight of this beam as 4.7 kilonewtons. Okay, this is the weight. The weight of the body or the weight of the person is applied at the centroid of this object. So for example, this weight will be somewhere here in the middle, and this weight will be applied like that. Okay, so this is our weight, and the weight is applied somewhere in the middle. So the middle of the section here, and the middle of the span. So the total weight is a point load. That's why it is in kilonewton. So the total weight of this beam is 4.7 kilonewton. But the question asks for unit weight per unit length. So how can we find the weight per unit length in this example? So the weight per unit length will be the weight of the object or the weight of the beam divided by the beam length. So we need to, instead of calculating the load at the point, if this is our beam, so we need to find the load distributed over this beam. So to distribute the load over the whole beam, we need to divide by the beam length. What is the beam length here? in this example, the beam length is L equal to 7.8 meter. So we divide the value we got, 4.7 divided by 7.8, we get a value of 0.52. Okay, so the weight per unit length equal to the weight divided by the length. So 4.7 times 7.8 give us a value of 0.52 kilonewton per meter. Is that okay? Do you understand the difference between weight and weight per unit length? Okay. Okay, so I think we can get a rest for 5 minutes. So we come back at 2:10. So we can have a quick rest for 5 minutes and then come back to the lecture. And I will pause the recording now. Okay, so the third type of loads we have is uniformly distributed area load. So we have uniformly distributed line load and uniformly distributed area load or pressure. So as you can see here in this example, if we have, for example, a roof or a slab, so in this case, the load will be distributed over the whole slab. So this means that the load will be distributed over the area of the slab or the area of the roof. So this type of load is also uniformly distributed, but instead of over a line, it is over an area. So the uniformly distributed area load or the pressure is a constant force applied across an entire surface area and can be expressed as force per unit area. So the line load or the uniformly distributed line load is force per unit length, and here is force per unit area. Okay, so the pressure equal to force by area. The unit of the pressure is kilonewton per squared meter, or in other terms, kPa, kilopascal. So kPa means kilo pascals. Okay, and please note that kilonewton per square meter and kilopascals are equal or are similar units, so you can use either of them. So this is uniformly distributed area load. The difference between area load and line load is again the uniformly distributed line load is distributed over the length. The pressure or the uniformly distributed area load is distributed over an area, similar to the area here of the slab or the area of the roof. And here is another example of calculation of load, as you can see here. So we have a slab, simple slab or simple roof, and we want to find the weight of this roof per unit area of the shown reinforced concrete slab. So we have a slab, the dimension of this slab 7 meter, 5 meter, and the thickness is 16 centimeter. So we need to find what is the unit weight per, the weight per unit area of this roof or this slab. So we will start similarly like before. We need to find what is the total weight of the element, which is the slab weight. So the slab weight is equal to the volume times the unit weight. We know before that the unit weight of the concrete is 24. So gamma for concrete is 24 kilonewton per cubic meter. So this already we know. So the volume of this slab will be the width, length, and thickness T or H. or height. So whatever the symbol is. So it is the 3-dimension. So LWH. So it is 7 meter times 5 meter times 16 over 100. We convert centimeter to meter because all the unit need to be consistent. So the total weight of this slab will be 134 times 0.4, or we can write it if we want to get it step by step. So 7 by 5 by 16. So the volume itself will be 5.6 meter cubed times 24, which is gamma, give us a value of 134.4 kilonewton. So this is how to find the slab weight. Now we need to find what is the weight per unit area of the slab. So the weight per unit area of the slab will be the slab weight over slab area. We already know the slab weight, which is 134.4. So the weight per unit area of slab will be the slab weight divided by the area of slab. What is the area of this slab? The width and times the length. So the width is 5, the length is 7. So the area of slab is 7 times 5, which is 35 meters. So we can write it down as 134.4 divided by 35 equal to 30.84. The main thing here is the unit, kilonewton per squared meter, because this is unit per area. So kilonewton per square meter is the final answer. Do you understand this formula or this calculation? Any of you has a question? Got a question? Thank you, Chuck. All good. So we have another method to find the unit weight or the weight per unit area of a slab. So another method is the weight per unit area will be equal to the thickness times the unit weight. So this will give it us quicker, but you still can use the first method, but just in case if you want to simplify the calculation. So the unit weight times the thickness will give us the weight per unit area of a slab. So what is the thickness? 16 centimeters. So divide by 100 to get it in meter times the unit weight which is 24. So this will give us same value, which is 33.84 kilonewton per squared meter. So these are two methods to find the weight per unit area of a slab or a roof or roof sheeting, because we will need this in our calculation. But just this is how to find it. Yes, all the unit weight are given, but not given directly. But if you go back a little bit, can you see here? Can you see the table now? Table A1. So using the material, because in the project you will assume the material, like for example roof sheeting. So you need to go to find the weight of this roof sheeting. So for example here, if I look at this one here, this is the concrete. So what is the value of the concrete unit weight per unit per cubic meter? 24. Okay, so you don't need to memorize what is the unit weight of the material, but you just need to know how to use the standard table to find the weight of the material. Another example we use today is the black butt timber. So what is the unit weight of the black butt timbers? 8.7 kilonewton per cubic meter. Right? So this is how to find the unit weights, which will be in the table A1 of the Australian Standard 1170.1. So this was example of slab. So now we can jump to another example, which is how to find the weight of the walls, for example. So what is the weight of walls? So we need to find what is the weight per unit area of the brick masonry burnt clay wall, and what is the wall total weight. So here is another hint. Here we have a hint to find the total weight, to find the weight per unit area. So here, structure design action, table A2. So this type of material will be found in table A2. And another thing difference here is this material is given, the weight of this material is given as force per unit area. Okay, so because this material, they already calculate the weight, so to make it easier for us, instead of weight per volume, they give us already for a specific thickness of the wall. So for example, they calculate for a 10 millimeter thickness. So they already consider the value of 10 millimeter thickness. So for example, when you look at table A1, you will not find the burnt clay wall, but you will find it in table A2. So in table A2, the material and the force per unit area. So kilonewton per square meter. So if we look at the table, we will find the brick masonry burnt clay wall per 10 millimeter of thickness. So the value is, sorry, not this one. It is this one here, per 10 millimeter of thickness. So what is the value? 0.19. So from the table, the weight per unit area is 0.19 kilonewton per square meter. But this, just to make note, that this is only for 10 millimeter of thickness. If I ask you what is the thickness of our wall here today, 15 centimeter. So the wall thickness is not 10 millimeter because 10 millimeter is very small. So the standard give us like a unit of the wall, like example of the wall, which is 10 millimeters. So you need to find how much it is for 15 centimeters. So how we will use that? So the wall weight per unit area is 19 millimeter per kilonewton, okay, times 15 times 10 millimeter. So here the problem is we have the thickness as centimeter, value of centimeter. So we need to convert it to millimeter. Why I convert it to millimeter? Because the standard give us the unit or the value for millimeter. So that you need to convert this 15 centimeter to millimeter. How to convert from centimeter to millimeter? 1 centimeter equal to 10 millimeter. So each centimeter has 10 millimeter inside. So we need to multiply by 10. So to convert from centimeter to millimeter, you need to multiply by 10. So that we have now 150 millimeter. So if we divide 150 millimeter times 10 millimeter multiplied by 19, this will give us the unit weight for 15 centimeter. Okay, it is like relativity analysis. So we have 10 millimeter thickness of the wall give us a unit weight of 19 kilonewton. 19 kilonewton per squared meter, right? So 150 millimeter will give us how much? X. So X is the multiplication of these two divided by 10. So X will be 150 times 0.19 divided by 10. It is like the thickness of this wall is 15 times the given thickness in the standard. So 150 over 10 is 15 times. So the wall weight per unit area will be 2.85 kilonewton per squared meter, or in other words, 2.85 kPa. Okay? Do you understand this one? I just want to confirm with you. If you want, I can repeat this one again. Do you understand this one? Okay, thank you guys for confirming. So we will use this method as well, because some of the material, as you can see, it can be given as kilonewton per squared meter for a specific or for a specified thickness, so that if the thickness is different, so you need to find for the given thickness. So again, it is 0.19 from the standard times the thickness of the wall over the thickness of the standard 10 millimeter. Okay, so this is the weight per unit area of the wall. Now, what is the total weight of the wall? So the total weight of the wall will be the wall weight per unit area times the wall area. What is the wall area? The wall area is this area here, which is 3.5 meter times 3 meter. So the total wall weight will be 2.85 kilonewton per square meter, which is the wall weight per unit area, times the area of the wall, which is 3.5 times 3. So the total weight of the area is 29.95 kilonewton. How this happen? So kilonewton per square meter times meter times meter. So meter with the meter, it is meter squared. So meter squared will omit the other meter square. So the product will be in kilonewton. So the weight per unit area is in kilonewton per square meter. The weight is in kilonewton. Okay. So this was another example of calculation of the weight and weight per unit area of the wall. So we can go now to the next part. So the next part will be some definition about the loads. What are type of loads? So the action or the loads and their effects. So what is the action? The action is any set of displacement or forces acting on an element or structure. And example of the actions or loads: weight, wind pressure, earthquakes, ground movement, waves, and so on. So this example here, we have a structure which is the electricity pole, and we have, due to the wind apply some pressure or some wind pressure on the pole. So that's why the pole has displaced like this. So any action that apply force or displacement on the element, it is considered as load. Examples again: weights, wind pressures, earthquakes, ground movement, and so on. And what is the action effect? Internal structure effect caused by action. So for example, when you have beam, you have load on this beam from structure 1. When you have load on the beam, you have bending moment and shear and so on. So bending moment and shear and so on, these are called action effect or straining actions. So some example of that is the bending moments or axial forces or shear force, which is the internal forces inside the member due to the loads. What is a design action? Design action is the value of action estimated for evaluation of performance before construction. So, for example, when you are designing a building, so you have some members like beams, column, and so on that we will have in this course. So, when you are designing a column, for example, you need to find what or how much is the loads on this member. So, the loads on this member are called design action or design loads. So the design loads are the loads that will be used to design or assess the performance of the members before construction, so that we make sure that the design is safe and economic. And here is again another reminder of the type of actions or type of loads we may have. So the type of loads we may have on a structure are dead load or permanent load, live load or imposed actions, wind load, earthquake loads, snow loads, temperature loads, loads on a structure during construction, similar to this one here. So during the construction of this building, for example, there was an equipment that need to stand on the roof to help in the construction or to lift something on the roof. So this is some example of the loads on a structure during the construction. And in our course, what we will be looking at is dead load, permanent action, live load or imposed action, and wind load. So all the others are not involved in our calculations, but this just to let you know what are possible type of loads you may have on a structure. So our focus on this course, will be only on dead load or permanent actions, live load or imposed actions, and wind load. Okay? Do you have any question, guys, before we proceed? Any question on the loads or on the calculations? Any question? Okay, so let's start with the permanent action or dead load. So the first type of load we may have on a structure is the permanent action or dead load. And the dead load in the standard gets the symbol G. So G refers to dead loads, and you can find the dead load in the Australian Standard 1170.1 section 2. So what is meant by permanent actions or dead loads? Permanent action or dead loads are the forces caused by the self-weight of the structure members. So this is the weight of the structure itself. Any structure or any building you construct need to at least carry itself first before adding any other loads like people load, furniture load, or whatever the use is. So any structure firstly need to sustain the self weight of its member. So you have, like, for example, here you have roof sheeting, you have beams, you have purlins. So all these members has own weight or self weight. So all this is called as permanent action or dead load. This self weight of the structure, including self weight of the structure itself, which include all structure members like cladding and again roof sheeting, beams, columns, purlins, bracing, and so on. Permanent partition or walls, if you have like partition, like gypsum board or brick walls or whatever the partitioning is. So this is also considered as dead load. Permanent equipment, fixtures and fittings, machinery, wiring, air conditioning, and so on. So anything that you consider it will not move frequently or it will stay on the structure for a long time is considered as dead load or permanent action. So to summarize this, the dead load are the load that always there as long as the structure is there. So the dead load are the load that don't or doesn't move on the structure. So it is always there as long as the structure is there. This is considered as dead loads. What is the probabilities of dead load? What is the characteristics of the permanent action G? So we have three types of dead load known. So we know them. So most manufactured building material. So if you know the material that you will be using in the structure or the construction, so you can know the self weight of it using, for example, table A1 and table A2 of the standard, or even given by the manufacturer himself. This is one of the things. So table or standard AS 1170.1 tabulates the densities and unit weight for common building materials. So this is what we have been doing at the beginning of the lecture. So you can use table A1 and A2 to find the self weight or the dead load of the material. Okay, some materials are not commonly used, so we can estimate them using the densities of the materials, dimensions, moisture content may vary. So, for example, the timber depend on the source of the timber, depend also on the moisture content of the timber, depend on if the timber seasoned or unseasoned. So all of this are some uncertainties in the material properties. So this can be considered as estimated. Also, we have some dead loads that is can be considered. Sorry, some loads that considered permanent, even they are not permanent because they are stay on the structure for longer duration. So maybe some in special cases you can consider some other loads as permanent if they are staying on the building for longer duration. Okay, so this is some characteristic of the dead load or permanent action on the building, and mainly in our course we will be dealing with the first one. So we will be using the Australian Standard 1170.1 table A1 and A2 to find the dead loads. And here is again, we have already used this before, but this is just to know how to use it again. So all the permanent action and dead load will be found in tables A1 and A2 in pages 19 to 21. So the unit weight of the material and constructions will be found here. Again, some examples: aluminium, concrete, so concrete, aluminium. For example, fiber cement sheet, if you are doing like ceiling or partitions, wall partition, and so on. So this is, for example, if it is uncompressed, so 14.2, for concrete 24, for aluminium 26.7. So table A1 and A2 give us some or the unit weight of the most common used construction materials in the Australian market. And here is table A2. Again, unit weight of material and construction. But the difference here, this one is for unit weight, but force per unit area, because it give it us for specific. The standard gives the value for us for specific thicknesses. Okay, so for example here, for ceiling, we have fibrous plaster for 10 millimeter thick. So if the plaster you are using is 10 millimeter thick, so you can use the value directly. But if the plaster you are using is more or less, so you need to use the relativity analysis to find how much is the value. For example, here for floor, we have, for example, like cinder concrete filling, for example, 25 millimeter thick. So the density is 0.43, or sorry, the force per unit area is 0.43, and so on. So all the material you might be using will be given here in the tables A1 and A2. So you don't need to memorize anything again. So if you use something in the project or in the final exam or in the tutorials, we will be referring to the Storyline standard, or maybe in the exam it will be given to you, but you don't need to memorize anything. Okay? Okay, so that's it for the lecture today. So do you have any question in the lecture before we jump to another thing? Do you have any question, guys? Any concern you have or anything you want to ask about the course? Thanks, Andy. Do you have any other do you have any question, guys? All good? So tomorrow in the tutorial classes, we will be working on dead load example calculation for roof. So we will calculate the dead load of the members of the roof, including like the roof deck or floor deck and the joists and the beams. So this will be tomorrow in the class. And I will stop sharing this one now and start sharing another thing. I want to introduce something to you. So if you go to assessment part, so I have just opened the superstructure project, select your group. We will start working on the project I will introduce the project from tomorrow to you, and you need to start working on forming the group. So we have up to next week to finalize the group. So here you have some like 17 group you can join. So we need, I think there are more than 17. So we need 3 per each group. So we have, I think, 36 group. So please add your name to group. So each group should be maximum of 3. And we will discuss if you want to list number, but I prefer not to make them 4, but we will do 4 and also special cases. So the optimum or the ideal number of members in a group is 3, and less or more we will discuss. You can discuss, send me email with the reason or what is the logic behind that, and I will discuss with you. Okay, so please use the tab, select your structure project group or superstructure project, select your group, use this link to finalize the groups. So we want to finalize the group by next week. Otherwise, I will add you randomly to the groups. So it is better to like manage with each other, arrange with each other with your friends or your the people you already have been working together before in other courses to make the group project work smoothly. So it is better to for you to select the group yourself rather than adding randomly to the group. Okay, do you have any question about the group? I will release the project details by tomorrow or by tonight, and we'll discuss with you tomorrow in the classes. Just like structure, can the note sheet for exam be done digitally and printed? I found it better. Okay, we will discuss this later, Jazir, but we can do that. No problem. Anyway, the exam will be online, so I don't know if structure 1 was online or face-to-face. Okay, guys, do you have any question for me today? Any other question? Yes, nah, we will have practice and we will have lecture in both component to review the last year exam. And the exam will not be much different from last year's exam. So week 12, we will assign it for the. We don't have the exam will be online, so I don't think you need the cheat sheet too. Yes, the exam up to now is online. Yes, okay. So structures 2 last year was online, and this year will be also online. Okay, thank you. Okay, thank you guys for attending today, and see you tomorrow. Thank you, Siog. Thank you, everyone. See you tomorrow.